Okay, Oliver will continue with foundations of matrix.
Thank you. So it's a second talk where I concentrate on the foundations that we saw yesterday and about applications in matrix here. So I put 3 theorems here of different natures. These are theorems about ternary matrix, and I want to explain them to you, and then I want to show you how to use this with structure insights into the foundation. So let me explain this theorem. So standing notation for the talk is M is a matrix of rank R with grounds at E, elements 1 to the n. So that's fixed context. Then the first theorem is something about realization spaces. Realization spaces are, S is a field, then it's the Grassmannian containing the Plücker vectors representing M, model the torus action. We have the diagonal torus acting on the Grassmannian, and that's typically called realization space or Sturmfeld, which is projective realization space. The first theorem that I want to explain, it's some funny relation between different fields. So if M is ternary, then the realization space over F8 is the projection with the product of the realization space over F4 and F5.
Sorry, that is what's F?
F is a field. Will be applied to this. Yeah.
And ternary means?
Ternary means representable over F3. Maybe I should write this here. Okay. The second theorem, I forgot to say everything is joint work with Matt Baker. So I'm collecting things from different papers.
That means isomorphic as what?
That's
It's a bijection. There's more structure on the background, but I mean, there cannot be an isomorphism of varieties because they're different base fields. Simply bijection.
So particularly if one of them on the right is empty, then consequently the other spaces are empty. Not
Yeah, precisely. And this is wrong without the assumption I'm just turning just a sanity check that there's some constant to it. The second one is about positively oriented matrix. So if M is ternary and positively orientable, then M is representable over all fields with a possible exception of F2. Okay. And in the third theorem, it's a theorem about Lorentzian polynomials. So for that, I denote LM. So Lorentzian polynomials will support M. So this means it's a polynomial. I use multi-index notation here. These are variables x1 to xn. And the exponent is a subset of E. So it's simply a polynomial with non-negative real coefficients, which are non-zero precisely if I is the basis of M. Yes.
Sorry, with theorem B, you're going to explain what positively orientable means? Or if that's later?
Yes, this means you can choose an ordering on E. So not the natural ordering, but you can reorder it somehow with some permutation. Such that if you take, do you know what orientable means? So orientable means you can choose a Grassmann-Plücker function like yesterday in the talk with values in the sign hyperfields plus minus 1 and 0. And then it says that you have an ordering here such that for every basis of M, this function evaluated in this basis is plus 1. That's it, is correct. I don't know if this no. Yeah, it's so I mean the points, pick your favorite of the three theorems, that's how you should deal with it. Pick the favorite one and wonder about how to prove that. So if you don't understand this one or this doesn't speak to you, pick theorem A or C. And what I want to show is that there's a common proof. I mean, these are consequences of the theorem about foundations.
What are K and L doing?
Okay, let me get back here. We're here. So Lm is a space of Lorentzian polynomials. And this is also stable under torus actions. Torus here are the positive reals to the n. So we can scale every Lorentzian polynomials, the coefficients, by positive reals. So it's scaled by some positive real depending on if the coordinates are in I. It's the same like the torus action of the Gaussian.
What do you call that a torus? Doesn't look much like a torus, right?
It's a group. It's a torus in this Pasture logic where I mean, this is the positive reals. It's a unit group of the tropical hyperfield, so it would be a torus over the tropical hyperfield, but that's just a side comment. Take it as a group, which I call torus for funny reasons. Okay, yeah. The Lorentzian polynomials always contain a particular vector, which I call chi-m, which is the generating function. So all coefficients are 1. I mean, whenever I is a basis. Okay. And then theorem C, this is joint work of with Matt and June and Mario Kummer. Is the following: if M is ternary, then the Lorentzian polynomials are homomorphic. I mean, this is a subset. We have real coefficients, so it's embedded in some R to the n, just taking coefficients. This is homomorphic to taking the orbit of the generating function times a half open interval to some power k times a disk with 3 points removed to some power L. Statement, right? Okay, so this is kind of the teaser for this talk, and in a sense, I want to explain you proofs at the end of this talk. And the way to do this is to study foundations and to develop the structural insight. So as the first point, since the foundations and Pastures part of the talk yesterday was quite quick, I kind of do a recap of that and do this with more calm that we all get. So I'm cheating once again. So just let me do this. Otherwise, I would spend too much time on that. But,
This is the low text slide.
Yeah.
You really must prepare for it because they go at human pace.
Sorry.
We want to encourage you to still go at human pace.
Yeah, I'm sorry for people who are writing. I know this is very unfair, but otherwise I couldn't do that and would have to be very brief on that and even know what it is.
Brains, not heads. Never mind.
Brains. Yeah, you know already what a pasture is from yesterday.
Brains, not brains.
Brains?
Brains, we need like our brains need to catch up.
Yeah, but your brains are prepared from yesterday. Okay, let's use the time from us. But you should slow me down I mean, seriously, slow me down, and I'm happy to end late with this talk and cut off parts of the second talk. We just have to see with the break because some people need to leave at 11. So a pasture, just to repeat this, it's a pointed monoid. So pointed monoid means it's a multiplicatively written monoid that's commutative and has an extra element 0, which multiplies everything to 0. Together with a null set in the group semaring, and this time it's a group semaring because for pasture, which is something like a field, the units are everything but 0. So these are finite formal sums of elements, non-zero elements. The null set is generated by three-term sums. This was a particular thing about pastures opposed to tracts. And this means, in other words, we can ignore sums with more than three terms, so with 4 more terms. This is a different way to introduce pastures, as Juni did in his talk, to just say we take 3 terms sums and we ignore the rest. So you're welcome to do that in your files.
Can you briefly comment on how restrictive this assumption is? I mean, I understand that all the examples you wrote yesterday are of this kind, but does one expect no interesting examples where you need 4 terms? Or it seems a little bit arbitrary to fix this 3 terms.
In a sense, yeah, I mean, it's not arbitrary because it's a profound insight. If you have a matroid and want to represent over a field or other perfect tracts, then you only need 3-term local relations. So there's a profound fact there. In a sense, you could reduce things to pastures, but to make sense of this reduction, you need to refer to tracts to have to deal with larger relations to reduce it. So I think, I mean, for this representations here, business of matrix, you can do it with pastures, and that's why we introduced them, because they're somehow simpler to deal with. They're also behaving differently categorically, so there's a mathematical advantage to it. But it's also just easier for people who don't know this algebraic geometry approach.
All of you here assume that M is ternary, so
yeah,
that presumably is needed for you to apply this, or is that something?
No. So ternary, we forget about ternary for the time being. I come back to this later. Now matrix M is just a general matrix. That's why I mention ternary always in the theorems, because it's not a standing assumption. And
so these have nothing to do with each other. 3 terms here, ternary there.
no.
Okay.
This is just coincidence. This has nothing to do.
But can you remind me, what type of object is NP? Is it a, like, what does generated as a what object?
So the correct answer is as a fusion ideal, but I will not tell you that. But think of it as an ideal. There's some subtlety which you can ignore if you follow this orange path, if you ignore higher term relations. But it's generated somehow as an ideal. But this is something that I can explain you later, but I don't want to be right now. Okay. Yeah, the third axiom is the existence of additive inverses. So every A and P has a unique minus A and P such that A minus A is an NP, where A minus A really means A plus this element minus A. Okay. So everybody's friends with pastures. Okay, here's a remark that yesterday on the blackboard, just to repeat, these axioms imply that -1 squared is 1, and minus A is -1 times A. So -1 acts as an involution of the elements. Okay, then last definition is that of a pasture morphism, which is the same as a band morphism, just to keep copy it down here. It's a multiplicative map from pasture P to pasture Q that preserves the constants and that preserves null sums. So whenever sum of AI is an FQ, then sum of the images is an FQ. Okay, then let me now do something new, or something that I didn't tell you yesterday. So pastures a very nice category. So we know fields, and fields are very nice algebraic objects, but the category of fields is kind of awkward. But raise your eyebrows, but awkward in the sense that you cannot compute limits and co-limits, arbitrary limits and co-limits. You don't have kind of, well, you have free objects maybe in a certain sense, but you cannot form quotients of fields. I mean, the only quotients, non-trivial quotients would be the zero ring, which is not a field. We can all do this with pastures. So it's much better behaved for constructions that we actually use what we're doing. So so the category of pastures is complete and co-complete. You can compute whatever limit and co-limit you have. In particular, it has products of two pastures. So product is just product in the category sense. This is, I assume that you're fine with settling or it has co-products.
Are you going to go through that for us in an example, or this is a theorem that you're suppressing?
I want to suppress this. I can comment on certain things, but I don't want to give you the explicit constructions. They're easy, but so the products would be simply the Cartesian product of the unit groups, and you throw back in the zero, and then relations in the node set have to be satisfied in each factor. So that's a construction. For products, I get away quite easy. The co-products are similarly easy, but a little bit hard because we form an amalgam of groups. So the co-products are right as a tensor product, similar as for rings. The co-product of rings is really tensor product over Z. And it also said it's complete and co-complete, so that it has an initial object, which we featured already yesterday, which is F1 plus minus. It's initial even in bands, so in particular it's initial in pastures. Initial means there's a unique morphism into every other pasture. And this, just to repeat it, has three elements, 0, 1, minus 1. And the node set F1 plus minus simply generate this one relation 1 minus 1. And then we take multiples of this relation. Okay. Now two constructions that are important, and I can, so let me say with co-product in words how to construct it. It's characterized by the universal property that's homorphism from here into some Q, just corresponds to pairs of morphisms from P1 to Q and P2 into Q. But its construction is you take the unit groups, take the direct sum, you quotient out the diagonal subgroup formed by 1 and plus minus 1. And then the node set is simply the smallest node set that contains relation from P1.
Oliver, I know you don't want to do this, but aren't you going to prove all these theorems by saying this is about tensor product?
Use categorical properties. I only use the categorical property of the co-product in proving theorems. So I never use the Tutte construction. It's like when a graduate student learns about tensor product. I mean, at least this was the way I learned it. I was told, well, at some point you will only use the universal property once you understood it. And that's the way I want to use this tensor product. I'm going to leave. Okay. So there are three extensions. And the three extensions, just to make this precise, I will explain the universal property. So I will only use three extension of F1 plus minus, the regular partial field. And so I take three extensions by a number of elements. I only need finite sets, but you could just take infinite sets of variables, of course. So the homorphisms of this free extension here, they're characterized by maps of the variables x1 to xr into P. So it's something like a polynomial ring, but there's one thing I need to take care of. The images are units. So it's more like a ring of Laurent polynomials. But in the world of pastures, this is really a pasture because it's, I mean, the construction would be not to take Laurent polynomials, but only monomials. So you don't add up things. But it's a free construction, a free algebra, but I call it extension to don't confuse it with polynomial rings because it's behaving a little different.
You're defining the left-hand side to be the right-hand side. Is that what the string is?
Sorry.
So this is a definition of home F1 plus or minus?
I think you're hiding Yone dilemma behind, like, right?
Sorry?
You're hiding Yone dilemma behind this definition. And you're telling us what are the morphisms to define the object.
I see. Okay.
I'm not sure.
I see. So you're defining. I see. This is meant to be a definition of F1 plus or minus of X1. Okay.
Yeah, define.
Telling us the morphisms, and on the right, the maps are what sort of the maps of meaning morphisms of.
These are simply maps of sets.
And so it's just these are just maps of sets. Okay.
So I define this object in terms of their universal property. You have to read this. This is factorial bijection.
I think what maybe many people are not so used to is that you're defining an object by saying what are morphisms from that object to be.
Yes, this is the thing in
That's what you
category theory, which I also used for band schemes yesterday. You can embed a category, so you're embedding into a functor category. And so I tell you what this guy does as a functor. It's a highbrow version. And that's the only thing that I will do so outside. And we can define functions. And they are characterized by the following universal property. The homomorphisms of a quotient. So I should say S is a subset of this group summary. So these are kind of sums. And then we can define quotients which I denote by that. It's kind of this double slash notation. Here we should think of, we take the ideal that's generated by it and we divide by the ideal. That's not really dividing by the ideal in this case, but we enrich the null set by more relations. That's what's really happening. So I don't use the double slash to make clear that's not really like taking literally a quotient of a ring. And this has the universal property that it represents the functor. Now I have to write this out in detail. Presents maps from P to Q such that for all terms in S, the sums of the images of these AIs is in the node set of Q. That's completely analogous to the universal property of a quotient of a ring, for example. Also for fields, but there are no quotients. Here we have quotients. Okay.
So the free extensions only exist for this F1 plus 1. Does that extend to, can I take a free extension of any?
They exist in general, but if I take something else than F1 plus minus, I would need to say something about linearity of maps. So I would say they're linear in this guy. So I want to avoid that and I only apply to F1 plus minus, but they exist in general. Yes. Okay. So let us review the examples from yesterday. Here is a pasture, and I just give you this directly because I first said rings are bands and fields are tracts and then fields are pastures. So here's a direct recipe. We take the field, we consider it as a point of moment. Then we define the node set as all formal sums such that these elements actually sum to zero. That's a pasture. It's a pasture because the addition of fields is defined in terms of three elements, a plus b equals c. Then we put in here a plus b minus c. And that generates.
But these are just not three-term sums or both?
You have these two ways of thinking about it. Either you just truncate it and you say your sums are contain at most three elements and read it like that. Or you say, well, you take really all sums and you take a node set instead of that. Yes, three-term sums generate, but I didn't quite tell you how they generate. That's the subtlety that's behind that. Here's a Krasner hyperfield. And I use now the new notation. So the Krasner hyperfield contains 0 and 1. So it's a quotient of the partial regular field. And what I do is I use the equation 1 plus 1, which forces 1 to be equal to minus 1. Because it's, I mean, here it says 1 is its own additive field. So this really kind of identifies elements, and then I throw in this three-term relations 1 plus 1 plus 1. And that happens to be the terminal object in Pastures.
Is it easy to say in general what the set or what it is for a quotient?
Sorry?
Do I want the model? Sorry. At least. Never mind.
What is the unit group of the quotient? That's the question. Explicitly.
Okay, it's a quotient of the unit group. And you're quotienting out only by two-term relations. If a plus b is in your set S, then you identify b with minus a. And that's so unit group of the quotient is the unit group of the original Pasture model. These relations that come from two terms. Here's a sign hyperfield in our new fancy way of writing things. So it takes a partial regular field, and the only extra relation is that 1 plus 1 minus 1. It's in the node set. So positive minus negative is in there. Here's something that I will not use in this talk, but since it's a very important object, the hyperfield. This is I use a Berkovich notation of using non-negative reals. So it's a non-negative real, so it's a multiplicative monoid. Then the node set is generated by this three-term relations a plus b, where the maximum is assumed twice. In other words, b is less or equal to a. And this, I mean, matroids over the tropical hyperfields are evaluated in matroids, and this connects to many things in tropical geometry. But yeah, uninteresting for this talk. And then the last guy that I want to introduce is near regular partial field. So that's a typo. This guy comes from a partial field, as the name suggests, which has a name. But as Pasture takes this incarnation, so it's generated by two elements, x and y. And here I can tell you, so this is as a monoid, it's just 0 together with all powers of x and y's, but we allow negative powers. So it's a free group of rank 2. And the node set is generated by this single relation x plus y minus 1. It should somehow remind you of a three-term Plücker relation. But of cross ratios. So we divide out one term to normalize to 1. Which brings me to the next part of the recap, namely on foundations. So I introduced it yesterday very briefly, and I don't know how much this settled, so I also have a recap for that.
Do you want these monomials to have like predictions also and so on?
Oh, yes, and you're totally right. Thank you. Oh, yeah, it's Z2 times the model. Yes. Okay, here's a recap on foundations. I phrased this also slightly in different terms and makes this more explicit what a foundation is. We start with pasture P, and then I say P representation of M. It's a term that I didn't use like this yesterday. Just define it for this talk now. We use these papers like this. This is a Grassmann-Plucker function, so it's just a function that has two properties. One is it's non-zero if and only if I is basis of M. So the pattern of the zero patterns of the Plucker coordinates correspond to M. And the second one is it satisfies all three-term Plucker relations. So don't ask for higher Plucker relations. Okay. So this is what I call P representation. And then we also have a torus acting on the P representation. So maybe I should say this torus is simply the group P star to the n. And it acts like the torus acts on the Grassmannian, or like this torus acts on the Lorentzian polynomials. If one entry Ti here, it multiplies all coefficients where I is an element of, where I is an element of the subsets, capital I. So Grassmann-Plucker relations are invariant under this multiplication because these two conditions are. So we can divide this out as a set. And this is what we call the realization space over the pasture. So now if you look back at the beginning, F could be P, because we know what Grassmannians over pastures are. And it's a modular space of matroids. It's band logic. Anyways, we just need to consider it as sets for this talk. So there's one remark. The realization space is functorial in P. So if you have a morphism from P to Q, we can send the class of the P representation to the class of the P representation composed with F. This delta goes to P, and we compose it, and we get a function Q. And then you can check directly that 1 and 2 are satisfied for this composition, and that it also behaves well with the torus actions. Doesn't depend on choice of representative. And then the foundation, sorry for doing this again, but it's defined by universal property. For our chosen M, there exists a unique pasture Fm, which we call the foundation of Fm, which represents this functor.
Can you tell us a little bit more about that?
Yeah, I can tell you the construction in words.
Maybe with a little bit of writing.
Okay.
Or in examples.
Examples will come in due time, plenty. But what you do first is to define something like the extended universal pasture, which is F1 plus minus together with all these variables, round brackets, variables for all bases of the matrix. This says basis. And divide off by three-term Plucker relations in the node setting. And then in here, you take the relation as a subpasture in here. That's closely related to the universal pastures that you saw yesterday in the talk. It's just not taking degree 0 part. And this here is a multi-degree 0 part. Equivalently, you can say Fm is generated by cross ratios. The universal extended universal pasture. So that's a construction in a nutshell. And then you check it represents this functor, and that's all what we need to prove this theorems. And for applications in general. So normally we don't get back to the constructions. But we do when we compute things. Yeah, so this is a little bit of my yes.
How injective is this assignment of foundations to matroids?
Foundations to matrix.
Like,
You mean matrix to foundation?
yeah, matrix of foundations.
This is not injective at all. So not every pasture has foundation, but many matrices have the same foundation. Many matrices even have the same universal pasture, but you have different universal pastures which have the same foundation. So it's simplifying things. But the good thing is the foundation, I mean, this is what this is saying. The foundation controls the representation theory. Up to torus action, that's torus action something trivial, which is data that we want to get rid of. And if the foundations of two matrices are equal, then this means that the representation theory is equal between these matrices. So it's more or less an if and only if statement, except then we have to look at all pastures and not only fields. Makes this things nice. Okay. When did I think so? Let's now do something new about foundations. So I will tell you a few theorems. Ask me again.
Somebody said the representation theory is equal. We have sets of the same size, like you're saying, if something's rigid, you mean you just get blocked off, that sort of thing.
Can you repeat that? Sorry.
So maybe I'll wait until you see. I think we're gonna come back to this.
So here's a proposition. Properties of foundations. First of all, the foundation of the dual of a matrix is canonically isomorphic to the foundation of a matrix. It's maybe not surprising because we know this dualization of Grossmanians and they somehow connect to residue fields. Another thing that's maybe reassuring is that the foundation of simplification is isomorphic to the foundation. Second property, which is something that I will use a bit, if we have a minor of n, so a minor means something we exclude some subset J, complex I, and I write this a minor to be embedded in M, and I call this embedded minor. Embedded minor means really we fix the subsets I and J, and I asked something in addition so that it's work. I is independent, and J is. But it's a theorem in matrix theory that every minor can be written this way. So the so-called scum theorem. I mean, if we have something that's not colon independent, we should move some elements to the other side without changing the isomorphism class of the minor.
How independent means complement is independent? What?
Yeah, it's independent in the dual matrix. Not the complement. Yeah, I guess. No, it's not the complement. So such a minor embedding induces a morphism from the foundation N to the foundation of M. And this is what you do is you take cross ratios here, and then you can, these cross ratios are ratios of two squares of Plücker coordinates, and you can augment the Plücker coordinates with elements in I, and you get a cross ratio here. So it's very explicit. There's not much to do. Just needs its conditions. It works. Here's one important observation. So we can get down. The foundation is very computable. Very computable means for small matrices up to 6 elements, I can think nowadays I can do it by hand. And we have a computer software where then can deal with larger ends. So this computer software is due to Justin Chen and Chenji Zhao. And you can compute the foundation for matrix up to maybe around 15 elements, depends on the complexity of the matrix. And you can do exhaustive search up to 8 element matrix, so you can ask the question, is a matrix with 8 elements with certain representation theory or certain behavior, certain foundation with properties, then you can just test it and it runs on a laptop, maybe in a few hours and give special answers. So,
What does it mean to compute it though?
to compute it means to find a representation in this way of 1 plus minus together with generators and together with relations. So we can compute a presentation, which may be a little ugly. And, I mean, in many cases, we had to massage this.
But actually, the definition you've literally written down is nothing to do. So what do you actually mean by compute? Like what sort of
What I just said.
what sort of answer do you want? But why don't we run? But what does that mean more than just know what the bases are?
So no multi-degree zero part, really new
I-
set of generators and relations, right?
I get the new set of generators and relations, which is smaller. I mean, I guess we can compute the basis for the unit group and the elements of the basis.
Can you then check equality? Can you check what you get is the cost nitrogen or something like that?
Yes, for small foundations, this becomes expensive. It's exponential in the number of generators. But in principle, yes, there's some feature in there we can compute, check for isomorphisms and for morphisms. Morphisms are interesting for representations, and isomorphism if we want to compare foundations. Yeah. Okay, I'm awfully slow, so let's see how I slow response through half of my time.
It should be very difficult to compute the home from pasture to pasture on set.
Yeah, if the unit group is large, it's very expensive. So
Like impossibly difficult,
Yeah.
So you just have to brute force it.
right? If you
yeah, you do brute force. There's some tricks to check for. I mean, you don't need basically you check for generators or check for fundamental elements, which are the things appearing here, x and y in 3-term Blocker relations, and these need to go to other fundamental elements and for pairs. And then you have some tricks to do smartly, but then at the end you just try for all combinations.
Right, so for example, computing home from the foundation to the rationals would be as difficult as like solving arbitrary Diophantine equation, which is believed to be impossible.
Yeah. So yeah. The rationals are not a finite object, so I think this we could not do with program in general itself. It's only possible for finite Pastures. Finitely generated Pastures, finitely presented actually. Okay, maybe I should ask you what we do now because I'm way too slow. So it's not for the planning. Should I conclude this story and cut short on the next talk, or should I try to wrap it up in the next 5 to 10 minutes here and do the other topic? I don't mind either.
What are our options?
Your interest? Do you want more on foundations, concluding that story, or the story about F1 geometry?
How hard is it to understand these theorems a bit more from what you've told us?
I mean, I went through half of my slides, but I have this kind of recaps. So I hope the second half is faster. But if you go on with the speed, it's maybe not.
Yeah, I mean, go as slow as you can.
Yep.
Yeah.
Okay, then let's do that. Then let's see, maybe let's make a break right now because some people want to leave, and this is now there comes really some big theorem that I need to explain.
Do you have any questions?
Yes,
I have a question about how the pastures fit in the category of tracks.
They're just literally on the nose tracks. We just
I understand that they are tracks, but
okay.
it seems like they have the same initial object, the same terminal object, and they have also product and co-product. So
Yeah, okay, so
are they inside of the
yeah, they are a reflective subcategory. So sit inside threads. And there's a reflection. So this is probably what's have to think about is. So I need to track on the right hand side. So the question making a track should be left joint. I think that's if I didn't make a mistake, but this means since we have an junction, they've preserved the co-product pastures inside tracks coincides, but products differ. I think equalizers are fine. So it's just products which are different. And that's something that we really take an advantage of. So for example, the proofs that I showed you yesterday in the end, the proof as it is works. Okay, process out, but for certain proofs, we really need this different products for pastures, which simplifies things. Okay. Yes.
Oh, you misspoke earlier. You were going to say finite pastures. Which one do you think? Sorry, finite foundations. Or question I want to ask was: do foundations of matroid ever? Like, how often are they finite?
They're always finitely presented, just by the very definition or by the construction.
So the question is, when are they finite?
Finite. I mean, if you have a uniform matrix, then you basically have three groups. This U appears as foundation of U24, the uniform matrix. So when you have more non-bases, you get more relations, and it's getting smaller. So I don't know if there's a very concise way to answering that, but if you have too many non-bases, it's just F1 plus minus. If you have a little more non-base, it's F2, but we know a lot of other finite pastures. So every finite field occurs as a foundation of some matrix, namely the projective geometry over this field of any degree. I mean, starting with 2, 3, 4, whatever. And there's another guy that shows up after the break, which is the hexagonal partial field, or the 6 root of unity partial field, which is finite. And I'm not so sure if we know other examples. Actually, the sine hyperfield is foundation, Krasner is a foundation. So they also show up.
So I was just wondering how flexible these pastures are. Like, this is some sort of Grassmannian over P, sort of. Can you do? Can you do other? I'm worried that if you want to use higher order relations, you won't be able to do it if you only allow. Oh, is it tracks?
Over tracks, you could do that. Yeah, but I don't want to do that, and that's why I simplify things pastures.
The relation between L, M, and the origins.
The space of Lorentzian polynomials, is it homeomorphic for realization space?
In this case, yes. I will explain this at the end.
Is it the case that a matrix is non-realizable over any field if only if the foundation is the cross type, cross the hyperfield?
No, there are other foundations. It's, for example, the sign hyperfield also appears as foundation of some matrix with 9 elements, and sign hyperfield doesn't map to a field. But there are also kind of extensions of the Krasner hyperfield that appear as foundations. Yes.
If two matroid are just one given by the circuit hyperpolarization by one another, then can he find any relation between foundation of two matroid?
Yeah, there are many relations. I mean, the kind of easiest types of relations, I think. But yeah, maybe I didn't understand construction, but there's also something that like delta y exchange, which doesn't change the foundation and generalizations of that.
You just talked about the circuit hyperplane relaxation.
Ah, okay. So this would be a weak map, right? Of matrix you use hyperplane relaxation.
Yes.
Yeah, then the answer is no. The foundations become very different if you do that, and there's not direct map.
Let's take a 10-minute break. Like we as a collective have decided that it would be better if we go in this slow pace and maybe Oliver finishes his stuff on foundations of matroids and not rush over F1 geometry and teeth string combinatorial like varieties. So we'll go in this pace and we will try to find the separate time for the third talk, and we're going to update you on when that will be. Yes.
Okay, now I want to explain you a very fundamental result on foundations, which basically starts all more serious applications, particularly to proof theorems. So for that, I need to introduce some things. So first of all, C5, this is just a notation for the serial extension of U to 4. That's a matrix on 5 elements where a serial extend one of these elements here. It's a rank 3 matrix. And the dual is a rank 2 matrix which is parallel extension. So the usual way of drawing it would be we have 2 parallel elements and
By this serial extension means what?
the other elements on the line.
The serial extension means what? We add a colon.
Another way of thinking that, if you don't know what a serial extension is the basis of this matrix C5. These are all 3 subsets of the 5 element set, except for one triple. Let's say 3, 4, 5. Yep. And this here correspondingly, all bases are 2 subsets except for the pair of these 2 elements. And then I denote by calligraphic EM the diagram of all embedded minors of certain types. So all embedded minors n of m, and just to repeat, embedded minors means a fixed j and I. It's really a tuple of j and I. Think of it to construct an of that. And I take those types. Types means morphism types, matrix of types U to 4, U to 5, root 3, 5, C5, C5 star, U24 plus U12, F7, and F7 star. So F7, this is a Fano matrix. There's 7 elements. F7 starts a dual of the Fano matrix, also on 7 elements. So we're considering all embedded minors of M of these types, and we turn this into a diagram of matrix by adding all minor embeddings. So whenever one of these n's of these types appears in another minor of M, which means just very down to earth, if I have a minor determined by I and j, and the second minor determined by I prime and j prime, whenever I prime and j prime are subsets of I and j respectively, then the first minor is this minor of the second one. Right? It's too confusing. With this obvious notion, if I take minus, I can take smaller minus, and then I get minor embeddings here. So it's just formally a diagram of minors and certain errors.
So you're using the word embedded just to remember the actual, or the actual what with the factor, or
Sorry.
what's the distinction for you between an embedded minor and a minor?
A minor usually is used just as an isomorphism class of some minor, but you don't fix I and j. So we want a more concise language, and we say embedded minor, precisely what I wrote there. Fix I and j, and I ask I to be independent, j to be growth independent. So what I want is that I get an induced morphism between foundations. U24 can, for example, appear in many different ways. It's a minor of something else. So U24 appears in 5 ways as a minor of U25. And I want all of these 5 ways to be different. Not just say U24 is a minor of U25. Okay. So then what we can do is we can take this diagram and take the foundations of all of these minors, and the minor embeddings give us Pastures morphisms. So this is applying the foundation functor to the diagram M. So this is the associated diagram of foundations and Pastures morphisms. Okay. And then here's a big theorem. Foundation of M, the colimit of this diagram. Told you before, we can compute arbitrary colimits. In particular, if M has the universal property of the colimit of this diagram.
Yeah, morphisms in this diagram are all coming from minor embeddings.
Yes.
You don't add.
No, I don't add more. They just come from minor embeddings. So it's a categorical statement, but it means you kind of follow this categorical approach. The representation theorem of M is completely determined by these very particular types of minors and how they are included in each other. So the first thing that we want to do is to ask, okay, what are these foundations of these minors? Do they do anything? That's something don't know, before those questions, nowadays I can do this for them by hand. I think in the beginning we did it by hand actually, and it was need some practice, but so the answer is very simple. This here is U. This here is a guy called V, which is, so V is a, let me define this in a moment, but then you can also forget about it because we want to avoid V. V is a bad guy for what we want to do. This is also V, it's just a dual minor, so it's not surprising. The simplification of C5 star is U to 4, so this is U. But this is a dual of C5 star, so it's also U. Something that I didn't tell you, but someone asked a question about that. The foundation of a direct sum of matrices is a tensor product of the foundations. This here is regular, so it's F1 plus minus, so it's trivial tensor product, so we end up with U once again. This foundation is something new, but something that we know. F2, and so we see the foundations are only 3 Pastures that are showing up. So even though the list is, what is it, 8 matrices, there are 8 matrices, there are only 3 isomorphism types, 3 building blocks that we need to compute the foundation. So let me briefly tell you what's so this is so-called 2 regular function field. But this field was introduced by the sample in connection with U25, but it didn't really make size, and then later Benaving van Zwaan proved that this is actually the universal partial field, and then it's automatically also the, knowing that the foundation is partial field, it's actually the foundation. This here is one presentation which I like because it's symmetric. It's generated by 5 variables over F1 plus minus, so its unit group is rank 5 times the sign. In the relations, there are 5 relations where I read the index cyclically. So it's xi plus xi minus 1, xi plus 1, minus 1. Where I ranges from 1 to 2. But I learned recently by talking to physicists like Early and others that Francis Brown uses all along.
Could you just rewrite that? The orange is hard to read. Or read it out. I can't read your indices.
The color is the problem.
Okay, so orange is good. So yeah. Second.
Okay, and the size is a problem as well. Can you just read?
It's not important.
No, it's important to me.
Okay.
Read it, please.
It's F1 plus minus the joint x1 to x5 modulo xi plus xi minus 1 times xi plus 1 minus 1. So but we will avoid this guy. It's more complicated just from the looks at it. And it's also structurally much more complicated because this leads to all these difficulties in representations. Let me.
How can I charge to think of this theorem? So where's the input of my concrete matroid? How does it enter to EM here? Or in this theorem?
EM, you look at embedded minors of it.
So I have my favorite matroid, and I look at all possible minors of these 7 particular small matroids.
Okay, precisely. And the minor embeddings are actually also, this is very simple. The only embeddings of one type into another is that U24 is included in all of these minors, sometimes in different ways. Otherwise, there are no minor embeddings. There are only very particular types of morphisms mapping U into other, this U into other U's via isomorphism.
So when I think about this as U24 is giving me the three-term blocker relations, and the other ones are telling me how they fit together, how different three-term blocker relations fit together.
In a sense, yes. So the first thing is quite exact. So this U24 is responsible for the three-term blocker relations. But remember, there was this relation x plus y minus 1. So actually, I want to talk about cross ratios, relations between cross ratios. And the other ones give multiplicative relations between cross. Well, these guys are different. They just say 1 is minus 1. It's present. So it's otherwise they don't do anything. But these guys here, all these 5 guys here, they relate cross ratios, different cross ratios. They say either their two cross ratios are equal or a triple product of cross ratios is 1. So the theorem here, maybe, so the proof uses, so the main ingredient, first of all, is Tutte's homotopy theorem. So that's what I meant yesterday, kind of the driving engine for all of our applications. It's the same as in many proofs, matrix theory, which goes back to Tutte's homotopy theorem. But to get through this description, we also use a result by Wenzel, which implies that the foundation is really generated by the cross ratios. So I gave you 2 descriptions, but there's really a result behind it. And there's a result by Gelfand, Rybnikov, and Stone, which gives a complete set of relations, multiplicative relations between cross ratios for the inner Tutte group. Then there's some kind of plus epsilon to really find out these minors. But so, I mean, our contribution is not the largest here in this list, probably the smallest one. But the theorem really takes into account a lot of material, but matrix theory. So it's something far non-trivial. And it's super useful. So I want to show you how to use these things. So the consequence of that is that we get an explicit description of Fm in terms, I mean, this is what I said in words, but let me write it down. Anyways, in terms of generators, which are cross ratios. So different generators are used in this nutshell definition. It means generators are not really contained in Fm, but cross ratios are. And relations. Relations between cross ratios that come from these types of matrices. It's a complete list of relations. But we don't need this for the present purpose, so I don't write it out because this would easily fill 1 or 2 blank points. Okay. So you're with me. So here are some consequences, which are also just stated theorem, and I will hint at how to prove something like that. So the first one, M is regular. So the first two items appeared yesterday already. M is regular if and only if M is a regular partial field. Second one is M is binary if and only if the foundation is a regular partial field, or and then now here comes the third part. I will see that this as well as here. M is ternary if and only if the foundation is a tensor product of finitely many building blocks, F1 to Fr, where F1 to Fr are one of four foundations, Pastures. It's either U, F3, the field with three elements. Then there are two new guys, D and H. Let me define them for you. So D is F1 plus minus together with a free element modulo a single relation, which is Z minus 1 minus 1. This is called the derivative partial field. As partial fields, that's also something that people were studying before, think Penrose and Franz one. And I mean, you should think of here, when is Z minus 1 minus 1 0? Yeah, I lost you. Should think of Z being the element 2.
We can't read them. Well, I can't read.
Sorry, yellow?
But yellow is normally good.
Yellow's better? Okay. I was avoiding green and blue because that's normally bad. I mean, you should think of it as 2. Then this would have all powers of 2 and also the negative powers of 2. There's elements. That's a little bit how to think of it. Only it's and the other guy, H, what we call the hexagonal partial field. This is often also called the 6 roots of unity partial field. And we redubbed it because this is kind of awkward notation we found, but it also comes from a well-known partial field. So this is also generated by one element. And we got 2 relations. One is Z cubed plus 1. It's a 2-term relation which says that Z cubed is the additive inverse of 1. And the other one is really something leading to cross ratios, which is Z squared, and now I do this down is right, minus Z plus 1. What's Z here? This is 2. One, two. This is a minimal polynomial for 6 root of unity. It's a 6 cyclotomic polynomial. So you should think of that. And then Z6 cubed is minus 1 usually. So this maybe makes sense. So for ternary matrix foundation, it's a little more complicated than regular and binary, but there are 4 building blocks. And let me say briefly how you prove that. So something that you will observe is that regular matrix, I mean, if M is regular, we check what kind of matrix can here as minors. A matrix that's regular is representable over every field. And none of these matrices are representable over every field. So we have null minus of types F2, U, and V. So this means this diagram is empty for regular matrix. So we take here a co-limit over an empty diagram, which is the initial object in the category F1 plus minus. This statement here, a matrix binary if and only if it's representable over F2. And if we check this list, we're left with these two guys. So we exclude U and V. And our diagram will be, I mean, there's no morphism between this F7 star, so the diagram will be just a bunch of points without morphisms. And foundation of each of these points are F2. So foundation is tensor product of several copies of F2. If it's empty, it's F1 plus minus, and otherwise F2, tensor F2 is F2. With ternary, we are also still lucky if we're checking. Can we say, well, not ternary, not ternary. These guys here are ternary. These guys are not ternary. So we again exclude different combinations of these guys. So F2, no. So our fundamental diagram just consists of minors of type U, and their morphisms. But all morphisms between U's are isomorphisms. We'll get kind of a directed graph of U's with isomorphisms. The only thing that can happen is that this graph has cycles, and we go around the cycle, we get non-trivial automorphism of U. So what we compute are quotients of U by automorphisms. And these are precisely the 4 quotients that you can get.
Can I come back to that thought? I just want to see if I understand your questions. Could you have told us the monoid is 6 roots of unity and NP is 1 plus zeta squared cubed is, and whatever else, I guess, and the sum of the squares.
I'm not quite sure. So you're asking.
You could have given us a description of this as a pasture, not as a quotient, by telling us.
Yes.
And would the mono be the 6 roots of unity there?
So this here would be 0 together with a group of 6 roots of unities, and the node set is generated by 6 roots of unity squared by 6 unity plus 1. And here we would have plus minus to the I with A and Z. And the node set of D is generated by minus 1 minus 1.
So D is a subpasture of Q and H is a subpasture of C.
Yes.
Give it best just to think of it as a subset.
Yeah. So how, and I'm still not understanding the generated, like, how do I see that zeta cubed plus is minus 1?
Sorry, is that?
So how do I see that somehow equates zeta cubed is minus 1?
Where are you now?
In your second version.
Yeah.
Yeah.
That 6 root of unity cubed is minus 1 if you consider it as the sub pasture of C.
I
mean it's encoded here. This mu 6 with mu 6. I mean the group generated by zeta 6 with zeta 6. Okay, sorry, yes, you're right. I'm sorry. Yeah. Right. I need to include that. Yeah. Sorry.
that theorem has yield a description of the forbidden minors of the matroids of the ternary matrix.
Yes. We're going ahead. So this is actually, I mean, Tutte started with the homotopy theorem because you want to compute regular minors for regular matrix. For binary matrix was known at that time and used that in the proof. One of these two, and then sorry, but that's not some, but he knew that and he wanted to conclude regular, so that's why he developed the homotopy theorem for, and that's his first application. It's his two papers that he has, first on the homotopy theorem, the second one where he characterized it. But we can just read it off. So if M is regular, then none of these are representable. So all of these minors are kind of forbidden, except that this here is a minor of all of these other guys. So we can, it's enough to count U24. So let's do this minus here are U24, F7 star, which was a major result by Tutte. So this kind of is maybe proof of concept that this theorem just is very effective to do things. So we just read off this explicit binary characterization instead of doing a lot of combinatorial proofs, which are somehow boxed in here. You can do the same here. So if it's binary, well, F7 star are okay, but these are all forbidden. This is minor of the others, so only U24 is left. And for ternary, if we do the same game, well, F7 star are not ternary. They're here. All the U types are ternary, so we are left with U25 and U35. It's also a big theorem per se, which uses Tutte's homotopy theorem, but from this form we can just read it off. Yes.
Is there a way to, from this diagram, to keep track of the characteristic of the pasture, of the foundation?
This is hard. I mean, all finite fields appear as foundations, as I said before, but the diagrams are really complicated. So you have, in particular, you have V minors, except for F2 and F3, it's different. I mean, for F2, it just takes Fano minor. For F3, yeah, it takes a projective ternary plane, but it's fairly easy. But then for larger finite fields, it's more complicated. I mean, it's possible to understand that, but it's not so easy. Okay. Any more questions, or you're ready for the proofs of the theorems? Okay, let me prove some. The proofs of the theorems are now simple applications of the third part. And just do them to showcase a little bit more how you can use that description of foundations to something. So proof of theorem A is as follows. So since F is ternary, we know that the foundation is isomorphic to tensor product of finitely many building blocks, where the FIs are one of these four pastures. Sorry, I wiped out the study. So and this means the realization space of M over some FQ which applies to F8, F4, F5. But this is equal to the homomorphisms from Fm to Fq by the defining property of the foundation. Foundation is a tensor product, but it's co-product, this tensor product, so we just the product of Hom spaces of this individual guys to Fq. And these guys, let's call them Ri of Fq. This for shorthand notation. And then all what we need to do is verify that Ri of F8 stays in bijection to Ri of F4 times Ri of F5 for all of these four types. So we just check this relation for each of the building blocks that show up here. And this is something that I don't do, which is will not do here now.
Is this
But it's
is this bijection sort of the same for all four cases, or is it like a different kind of thing for each four cases?
so it depends on the bijection depends on this identification of F8 minus 0 and 1 minus F5 minus 0 and 1 times F4 minus 0 and 1. And well, this has to be a relation that respects relations between cross ratios in a certain way. So we choose some identification, and yeah, there's a choice. There's some symmetry group acting here on cross ratios. Yeah, so but we can choose some bijection here, whereas choice involved, and this bijection determines these projections over there. There's a little bit of choice involved, but not much. And this holds in particular for all m's. And this choice uses bijections for all m.
So you are equals in this theorem. You really mean equals.
Yeah, this isomorphism.
So then this bijection will also depend on the choice of isomorphism.
I think not. I mean, this choice of isomorphism would affect both sides here. And you just need to check that this identification induces identification between the Hom sets where Fi is one of the three guys. But homomorphism here doesn't strip this identification. Let's think.
I mean, up here, there's also a choice on how you split as a tensor product.
Yeah, splitting is canonically given. So it's given by the minus, by the fundamental diagram. Factors F3 might appear. You cannot track down by the isomorphism types the number of F3 factors is a little particular. The other factors you can track down. But I mean, this isomorphism is given by the minus of m. But to this here really isomorphism class of Pastures or model or automorphisms of this guy. So this is something we need to check, but I think this isomorphism doesn't depend on automorphisms here.
Do you have a good, what's a good example of Matroid to sort of see this in action? Do you have a favorite Matroid?
You mean to compute that?
Yeah, with small, we're think about the realization
I mean,
spaces by hand and actually seen.
U24, I think, is the best thing to compute things by hand, but I wouldn't like to do this now.
Some of the interesting there, right? The realization spaces.
Hmm?
The realization spaces is a bit interesting. That's just, then that's just what you said there. I'd like to see one that's a bit more.
No, you want to see an explicit computation of the foundation, or
Well, I
you want to have
what you do now. Okay, so that's what sounds like, this is not the way you think about it, so you don't think about it.
In questions about theorem A, where we can see the product of the relation space for some example.
So I agree, U24, you can see it, because but for U24, it's just the statement that six is the, whatever, that six is 2 times. There's no real, really. Yeah.
Okay, I'm still not understanding. You want to see
I want a
Proof?
slightly, a less trivial realization space where you could see this.
where you don't have a ternary matrix.
No, a ternary matrix. Don't worry, it's clearly, this is about this conversation.
Yeah, okay, ask me afterwards and I'm happy to discuss this. Okay, so I just need this statement so I can erase this black box. Pictures of I prepared for the third lecture and that's I'm not getting to that part today. So the proof of theorem B is as follows. So again, M tensor products are factors of this type, and then well, we want to prove that M is representable over every field with greater or equal 3 elements. So say F is a field, F is maybe 2 over the so let's say K is a field. So actually, yeah, I don't use this for now. I'm using now that M is orientable, so I drop the positively orientable for now. And then I check that we repeat this here. Fi is one of these guys. U that is related E and H. So then I check. F3 does not have morphism to the sign hyperfield. Here you and just think about it. These are the things that I leave out are really easily verified, particularly this you can do as an exercise. Preserves 1 and -1, and then the relatives in here don't match up. H also doesn't have morphism to the sign hyperfield. It's maybe a little harder, but we can get this out. D actually has morphism to the sign hyperfield. And this kind of refers to a theorem that's known. A ternary and orientable matrix can be represented over every field that's not of characteristic 2. That's a theorem probably by Matroids, I don't know. And we would recover this by this method because D is represented as a map into every morphism not equal to characteristic D, invert 2. And U also goes in maps to every field not of characteristic 2. The foundation is tensor product of these and we recover that. If we add positively orientable, then you don't get a morphism here. And this is somehow, yeah, I will not prove this here because it's going into much detail, but if you have a cycle in this fundamental diagram, then the positive orientation kind of makes the cycle so rigid that the defining automorphism that gets you down to D cannot happen. So the positive orientation says the fundamental, that's D. Sorry, so this is wrong. So this says that Fi is not isomorphic to D for any of the i's. That's a conclusion. This is wrong. So what we conclude is that Fm is actually a tensor power of U, copies of U, and U maps into every field with at least 3 elements. It doesn't map to F3. So Fm happens to be regular, it maps to F2, but otherwise it needs 3 elements. And you can map from one tensor factor into Q. Okay, you can map from the tensor power.
What was positively oriented?
Sorry?
What was positively oriented? What was the positive?
This means if you take, do you know what the carotope is? So you can find an ordering of your ground set such that your carotope takes positive values. It's reflecting this ordering or non-negative values.
Is that always is that always true for realizable? Sorry, go ahead with this.
I'm saying, is that the same as saying that some reordering of the matrix is a polytroid?
Yes, I think so, yeah. Yeah. Theorem C follows a similar strategy. So it uses the result that I will not explain here, but if you have been in June's lecture, you will have heard that. So if you take the Lorentzian polynomials model as a torus, then this is equal to really the, I mean, one of the main ingredients here, which is joint work. It's June, Mario, and Matt. So this is a realization space of a certain Pastures 1, 2, which is a 2 triangular hyperfield. I mean, you use here that there's no U to 5 minor for makes this true. If there U to 5 minors, Lorentzian polynomials, they're more defining relations, and it's not literally true. Like, topologically, they're homeomorphic. And there's a kind of sandwich theorem for other triangular hyperfields. Never mind that. So let me find you T2. So this is are the non-negative fields. And the node set, this is generated by all methods A plus B C, such that square root of A, right? Square root of A, square root of B, square root of C has a side length of a Euclidean triangle. very funny relation. But this comes just a historical note. So Oliveira introduced these hyperfields. So this is something we would call the two triangular hyperfield. So Oliveira introduced the triangular hyperfield where you don't have exponents. You see here's the exponent 1/2, which reflects this. And he observed that these hyperfields kind of correspond to amoeba in a certain sense. And then if you take the limit q goes to 0, the Hausdorff limit of this amoeba gives tropicalization. So T0 in this logic becomes a tropical hyperfield. Well, for us, for this proof, T2 is the main type. And it's a very funny relation here. Let's just use it. So you can identify the Lorentzian polynomials model torus actually with the realization space, and then can continue. But this here simply homomorphisms from the foundation in T2. And this is over these factors, homomorphisms from ZFIs into T2. So this reduces the problem just, but the Lorentzian model is a torus. It's a product of certain spaces, which are homomorphisms from this building blocks into T2. So let's look at them. What's happening? Take homomorphisms from Fi into T2, where Fi is F3 per H. And there's only one morphism which maps everything to 1. Okay. If we look at homomorphisms from D to T2, then it's still there. We have the relation Z minus 1 minus 1. Here, if you think about it, I mean, the triangle can be degenerate, so two side lengths can be equal. And third one could be 0 then. So the additive inverse of 1 is 1. So minus 1 is plus 1 here. It's like in the tropical setting. So the signs don't matter much. So you need the relation that Z, 1 and 1 form the side lengths of a triangle, which means that Z has to be less or equal to 2, can be arbitrarily small, but not 0. So this gives us this half interval. So this would be in this logic 2, it would be 0. This is interval from this would be a natural choice of half interval. And then so homomorphisms.
Why is 2 okay, but 0 is not?
Because Z is invertible in D, so it has to go to invertible element here. This is the element of D star. And we're looking here at the image of Z. So D.
I'm just thinking that 1, 1, 2 is sort of a degenerate phrase.
It's degenerate. Degenerate is okay. So when I say triangle, it can be degenerate.
I see. Okay. So 1, 1, 0 is also a triangle.
It's also a triangle. And this is allowed as a relation here.
Okay.
But this particular element Z has to go to unique because it's vertical.
Thank you.
And this here, I mean, if we use this multiplicative relations, it's really 2. You remember it says x plus y minus 1. And if you map x and y into here, so x, y axis, you see, this is a picture that June showed us. It's something like this here. Then at infinity, kind of, it closes up. And then, I mean, take log coordinates, then you get a picture that's you're much more familiar with, which is the this kind of lines, the standard equation for the tropical line. So in here you have the propagation of the sky, and then just 3 points at infinity. So and these are, I mean, if we look back here, we modded out the torus, so this thing is taken care of by modding out the torus. This here comes from factors D in the foundation, so we get a couple of factors of this topological type, and then get a couple of factors of this topological type. Okay, I think that's all I need to say. Time for questions?
Is there any hope to characterize quaternary field of Morel?
I don't know, this gets hard because then we also get V's in there. If there are U2-3s and U2-5s and U3-5s, then it can be very complicated.
But we know some excluded minors, so.
You know the exclude minors, which is a very hard theorem. It's probably one of the hardest in matrix literature. Yeah, I don't know. I mean, it should be possible to prove it along these ways, but certainly not as easy as the theorems that I explained to you here. Yes.
For theorem A, do you know if like 4, 5, and 8 are the only finite fields where this works?
Now, my conjecture, this is there are infinitely many primes, so the condition is can replace by Q, P, maybe PQ and R, such that R minus 2 is equal to minus 3 times 2 minus 2, and 3 does not divide QR, and I computed them up to 200. So prime powers, so QR prime powers. And it looks like they're infinite many. You find more and more and more. And I asked Gonzague if they're infinitely many, and he came up with some heuristics of how primes are distributed and so on, which indicate there should be more and more solutions.
Are you saying all such PQR work and you're conjecturing that there are?
Yeah, whenever you have prime powers PQR with these relations, then this here holds. But the proof is then a little more. It goes a little bit more into that.
Checking those words. I mean,
I know that's validity.
you gave us the U proof basically. It's just checking the other or.
Yeah, it's basically checking that, but well, the things that are skipped here to say that you just need to check that for this fixed primes. I think it's an exercise. You can do that. If you want to do this for all triples, then you need more structural insights of how these morphisms work. Then you need to look at 6 tuples of cross ratios and how they correspond and what these 6 tuples each have. So it's a little bit more stable behind it.
What's the next triple here?
Exercise. It's not. Maybe I think of it in 2 minutes.
How do we see the sphere with 3 punctures? Is that from the log picture?
You mean this sphere?
Yeah, yeah, yeah.
Yeah, I do it as a sphere because here it's really kind of a ball. I mean, if your pictures maybe bad, if you take this is embedded into P2, so I'm taking the x, y, x, and here's if you homogenize this, then it's really giving by quadratic relation. So it's really in the right thing, it's a ball. But if I take log coordinates, everything becomes hyperbolic. Yeah, I don't know if it's not hyperbolic, but comes this picture which we are much more used to from the geometry.
Thank you. I have a very stupid question. Why does RMT2 even have a topology? I mean, of course, the pictures are very nice because these are positive, comes with topology, but
It's a semi-algebraic set. In a natural way.
okay, but this is because T2 you take in with R plus and you can throw it there.
So let's take this here. This guy is generated by cross ratios. So this is something like the form 1 plus minus. Generators, let me use xi's for cross ratios. And I model some relations. So the xi's, where it's specified in it set, this gives us an embedding into here to the I. So the cross ratios are the coordinates. And these relations for the triangular hyperfield give you inequalities. Triangle is determined by 3 inequalities. So each relation gives you 3 inequalities. So you end up with a semi-algebraic set in here, which has topology.
But this is like a super special feature of T2, right? I mean, in general.
Yeah. Okay, there's a more general thing, which is if your pasture carries it. So let's go back. If you like working with complex varieties, maybe, then you know have a topology. And this topologizes your variety. Same happens for real numbers, for p-adic fields, if you like that, for adelic points. And this kind of where you can also, there's an abstract nonsense category definition of that. Whenever your pasture carries a topology, you have a way to topologize this using topology. And here you would take just the topology of the non-negative real, the natural one, and then topologize in the way that this is related.
Risky topology is an algebraically closed field.
Yeah, then you take topology just, I mean, your finite sets are closed, for example. Or you just say 0 is closed.
And that induces the Zariski topology on the realization space.
I was now talking about the classical field where it's defined, but you could say this by definition, this is everything. I don't know.
But like if I have an algebraically closed field and there's a topology on the space, there's the Hom space, the Zariski topology.
Right. Repeat, I got confused now with this case and the other one.
So if
you want to talk about this case or?
No, like the realization space of a matroid over an algebraically closed field, like the k-bar points as a topology, the Zariski topology.
Yeah.
So can you get that from what you're saying?
Yeah. You just say you topologize your field with, it's enough to say 0 is a closed set, an empty set in the whole space, or you say finite sets of closed with the same result. Funny thing is, it's not a topological field set, but still, this abstract nonsense works and gives us an unexpected result.
Any other questions? Yeah. Now let's thank you again.